All right, hit recording. So we are now live, also for the people who will come after us. Today we will talk about linear regressions in a Bayes setting, centered around the chapter on geocentric models in the Rethinking book. And I'll just share my screen for my summary. And there we go. I'm just going to go right into this since we've got two new members today. I don't know how much you've heard about how we run these things. Just as a quick intro to you guys, the people in the recording will have already known this from previous recordings. Usually in the beginning of these, one of us, usually me, gives a short recap PowerPoint-wise of what the chapter and the lectures were about. Then feel free to interrupt me at any given point in time if you have any questions on what I'm explaining, what the chapter was explaining. I cannot guarantee I'll have the answer, but I hope someone in the room will. And once we're done with the summary, everyone else gets to weigh in on stuff that's not quite necessarily a question right in the presentation itself, and then we just mosey on over to the practical exercise stuff, where we just go through what the book has as practical stuff at the end of each chapter, and then we go through our respective solutions by screen sharing back and forth a bit. And there comes Ollie from the waiting room. Glad to have you, Ollie. Just going to get into the summary here. So today, talk about linear regressions in the Bayes setting. And first thing we get into is the modeling language. This is something I've seen in a lot of papers so far, but I'm really glad that now it's getting explained in this book. So I like how he builds this up from the ground, where the modeling language itself consists of variables and the variable associations, which then funnel into generative models. So with variables, these are the things we want to understand. They come in two flavor profiles. One is the data, meaning the observed stuff that we want to feed to the model. The other is parameters, which define associations between the different data sets, for example, or data variables. And these are unobserved. We want to estimate these. So like I already said, variable associations, which come after variable definitions, tell us how certain characteristics link with one another. These are probability distributions or equations that explain variables with other variables. Together, these then form a joint generative model. You should be seeing my mouse. If not, just tell me. So this over here is us explaining variables and parameters. And then this over here, sorry, these are just more variables and parameters. I will have a specification for a joint generative model on the next slide, I think. If not that, then the next slide thereafter. So to take a step back from this was just how we will look at the different model specifications in the realm of this book and hopefully our research going forward. Regressions, which is the core theme of today's session, are inherently descriptively accurate because that's how we design them to be. But usually, as far as nature's concerned, they are mechanistically wrong because they give us nice and oftentimes very accurate predictions, but they don't necessarily identify the cause underlying pattern or process or distribution that is out there in nature. That might not necessarily be a problem for us because we might be happy with accurate predictions. However, we might not have the actual understanding. So McElrath states that regressions should only be used for approximation instead of uncovering the ultimate truth about nature. When we talk about linear regression, so today's topic, we are always bound somewhat to normality or normal distributions or Gaussian distributions. These are lovely because they're easy to do math with because you can usually reduce the information to mean and variance. And they're also common in nature. So we can approach this from two sides. One is we like them because they're easy. The other is we use them because they're frequent in nature. And the reason they're common out there is because processes with fluctuations create a dampening effect because fluctuations can go in opposite directions, which cancel each other out. The dampened fluctuations themselves then create Gaussian distributions because everything tends to converge on a mean with a flattening distribution around it. However, important to point out here again, once we have these Gaussian distributions, which we explain just by their mean and their standard deviation, we lose all information about any potential underlying process. We still know the outcome of underlying processes, but the process itself is lost in this, which brings us back to mechanistically wrong, but descriptively accurate. So to go forth from regressions and normality itself, we have everything ready to go into linear regression. And for that, first thing we look at is the theory. Models of linear regression types give us some information about the mean and the variance of a normally distributed variable. The mean is modeled as an additive combination of weighted variables, so that's where linear oftentimes gets misunderstood as there's a straight line in a plot if we put something down. Linear just means we add stuff together. And it also comes with an assumption of constant variance, which oftentimes in nature might not be the case, but we're going to talk about that in the next few sessions. So let's not worry about that for now. The example that was in the chapter and in the lecture and will be here again was height as a function of weight. In this example, we're looking at just adults because that's where we find a nice straight line. So for now, we are running with a straight line. Here we get the model specification saying that the outcome, our height, is a normal distribution or is normally distributed around a mean with a standard deviation. We then feed that some priors just to understand the height distribution. So the important thing here is that we have not added any data yet, but already our model is making some very, very poignant assumptions about what nature is like, what the height distribution in nature is like. So the important bit here is that even without data, our model already has an idea of what the world might be like. And we should make sure that that expectation that is inbuilt into the model, A, fits with what we wanted it to be, because we may have misspecified something, and B, makes sense biologically. So the reason we do prior predictive distributions, which is exactly what this does, is to investigate what the model expects and also catch potential misspecifications or biological nonsense. The way we do this is by sampling from the prior distribution and then plotting and investigating. So a lot like we did posterior predictive distribution checks, which we covered in the last session. So if you're somewhat ambiguous about that, we can go back to that. If you're right here now in the room, just ask about it. So the important thing to take away from this is that uninformative priors often create impossible outcomes in our model expectations, meaning we can certainly do better once we input priors which are better suited to giving us biologically feasible expectations. The example that the lecture and the book ran with was modeling height and the uninformative priors, which you can see on the right-hand side, allowing for height distribution in the negatives, which by definition of how height works cannot be, because 0 in height always means absence of the measured value. So the point of origin means there's nothing there. Now, moving on from this, we want to, again, approximate our posterior distribution. And last time we used grid approximation, which quite handy, but at times a bit cumbersome, I have to say, because you have to establish different arguments and such to have your different intervals. So I'm glad we're going to move away from this here today. With grid approximation, we want to look at our posterior distribution in certain intervals which we define. However, oftentimes these posterior distributions are multidimensional, and then drawing a grid, even just on 2 dimensions, let alone 3 or more than that, can become computationally quite expensive. So the way this is done in the lecture and the book, what we do is we identify a sequence for our average height. We identify a sequence for our standard deviation of the height. So those are just the grid intervals. We then combine those into a grid matrix. What we then do is we obtain the likelihood for our heights. This is done on a log scale, which is very important in just a second. And that took me a very long time to figure out when I was reading this code, because I couldn't for the life of me figure out why the unstandardized posterior distribution was created by summing the likelihood with the priors. And so the reason why they are summing here is because summing logarithmic outputs is the same as multiplying non-logarithmic outputs. And that's why we do the summation here and obtain everything that's this true argument here on a logarithmic scale. We then standardize the predictor just as we have already done, and we get our estimate. That's how we do grid approximation for two-dimensional spaces. Now, it's not recommended to do that even in two-dimensional spaces. It might just be useful for a learning exercise. I would always move to quadratic approximation, which we talked about last time. And we're going to talk about right now as well. So this works exceedingly well for every model where the posterior distribution is Gaussian in every dimension. That might not always be the case, and that's when I assume we're going to move to MCME samplers. However, for now, we're just stuck with grid approximation, for better or for worse. Grid approximation works by way of walking along a distribution and then stopping when it reaches the summit, and describing the distribution just by the summit and the slope around it, which means it's much, much faster than a grid approximation on large dimensions and sample sizes. So the estimation here uses the peak of the posterior, which is also the maximum a posteriori, or MAP, and it looks at standard deviations and the correlations of parameters, which could give us a covariance matrix of the different parameters in the different dimensions. This, if using a flat prior, so an uninformative one, would be the same as the maximum likelihood fitting method, which we know from frequentist statistics. Now, on the right-hand side, you can see how this is done in R with the QUAP or QUAP function from the rethinking package, which has to be fed a list argument, which is written in very similar notation to how we write our model specification in math notation. We then obtain the precise sample from the posterior, or the precise understanding of where it estimates our certain parameters to be with the precis function. And here's the first question I have, because I didn't read this and didn't have the time to play around with it a bit. This 89% interval here, is that a percentile interval, or is that a highest posterior density interval? Did one of you check that? And if not, then that's fine. We'll just check it later together in the practical part of this.
Actually, I didn't check it, but I remember that from the video, he was always talking about percentiles. So I'm guessing that's what he means, but I'm not sure.
Yeah, I assume so too. I just really want to make sure, but thank you. Moving on, quadratic approximation can also make use of starting values, which unfortunately we haven't done in the lecture too much, or in the book, and not in the practical section either, at least from how I answered it. But I think this could be used to really speed the process of the approximation up quite a bit by starting the approximation at some mean of the data, for example, to make it easier to find the posterior maximum and the standard deviation around it. Now, what we've done so far is not really a regression, because we want to explain one thing by another. And to do that, we need to add predictors. One of them, or we have to do two things here. One is to define parameters. There, we still have our likelihood, we still have our parameters, which we have already defined previously, but now we've added the beta parameter, which is normal distributed, mean of 0, 10 of standard deviation of 10, and we also get our linear model, which is deterministic in nature. Everything in here is stochastic, everything with this tilde, but this right here with the equal sign, that's deterministic, meaning there's no uncertainty left. We know that, or we postulate that explaining the mean here, so that's the mean height, is as easy as having this alpha, the intercept, plus whatever parameter this is, times the weight minus the average of the weight, which is just standardizing stuff. Sorry, no, this is not standardizing stuff. This specification here just means that alpha is the height of the individual when the weight is the mean of all weights. That is how you would read this. So usually in linear regressions, you would understand alpha as the height when weight is 0, which doesn't make sense to begin with. Here you interpret it a tiny bit differently. So to add the predictor variable itself, we can then look at this linear model specification a bit more in detail. And we can identify right here what I said with alpha, for example, being the mean height when the weight of one individual is the average weight of all individuals. I think I've already went through this. I can flick back to this if you need me to. But once we look at our added predictors, again, I would like to look at prior predictive checks or prior predictive distributions. So when we use a naive prior for our beta parameter, this of course can vary wildly, and we might get negative relationships between weight and height, which to begin with doesn't really make sense for me. You would expect that overall there should be an increase in height as weight increases in humans, but most importantly, you can see that these lines here fall right outside sensible boundaries. So you would expect humans who are much smaller than 0 centimeters tall, which even at conception they aren't. And you would also expect humans which are giants, which from a D&D setting might be very interesting, but in real life just isn't the case. So getting this scatter right in your predictive distributions, prior predictive distributions that is very important. And the way to do this for this one example would be to, among other ways of how to do this, would be to use a log normal prior for beta, which is that slope that we're looking at. So with this log normal distribution, we force our distribution to be positive only. And already you can see that this scatter right here makes a lot more sense. And this is the core of what we use prior predictive distribution checks for, to get a better understanding of what the model expects and whether that makes sense. Now, the final linear model specification that we have right here is just loading the data, selecting the adults who we have here. We input our list, which we've already identified previously. The important thing I want to point out here is that when we specify these lists with deterministic functions in R, so linear regression, for example, the equal sign of math notation turns into this reverse arrow, which we already know from R when we assign objects. And that's important to keep in mind because this is how it'll work. Now, once we've got our model, there will be uncertainty. And from the first session that we had, and we all talked about what we were most interested in, I'm sure Gregor was very fascinated with all of the prior distribution check stuff in this chapter. I was elated when I saw this much about uncertainty, because the important thing to remember about uncertainty is that there's uncertainty about our parameter estimates, but then there is also uncertainty about our predictions. And the uncertainty about the prediction incorporates the uncertainty of all of the parameter estimates. So it's usually, well, always, a lot larger than the individual parameter uncertainties, unless you have one parameter which is super uncertain and everything else is very certain. Then there won't be that large a discrepancy. Now, to get our uncertainties about the single parameters, we can, for example, use the PRECISE function, which gives us a single output. However, a more Bayes way of seeing the world would be to draw samples. So we can use the function extract samples from the rethinking package to get a number of sample outputs, which visualized right here, then allow us to plot some nice figures. And I personally just like figures because it makes it much easier for me to understand what the model is actually doing. So tracking the uncertainty makes for far more informative results. We may find, and this may just be a pet peeve of mine, that our results become less statistically significant, very big air quotes on that one. However, I would like to argue that it is honest science to report the actual uncertainty you have associated with a certain result, rather than making a binary decision of statistically significant or not. And I think we could all do a lot better if we were to start tracking uncertainties in different data sources and how we handle those data sources. But that's just a pet peeve of mine because I work with climate data, and that's a whole nother can of worms in itself when it comes to uncertainty. So what we're interested in with the uncertainty itself is not necessarily how big it is, but the shape of it in our prediction interval, because that will tell us much more intuitively where our model is doing well and where it isn't. So for example, if we have a cone in it, that might be a finding which we might want to investigate somewhat further. So to get all of those predictions with our uncertainty, like I already said, predictions incorporate all uncertainties. The way to get these with the rethinking package is to get some new data in on which to do predictions, and then just use the sim function for simulate, I guess, which then lets us plot these really nice wide boundaries on the right-hand side here, where you can see the underlying data, then you can see that black trend line, a dark shaded area right around it, which is just parameter uncertainties, and then you get the full prediction uncertainty with this very wide corridor. And to me, that's quite compelling to see this much uncertainty around it, because it tells me much more about how well, for lack of a better word, certain I can be of my model. So having looked at this, we have considered the linear model to be purely linear so far. However, sometimes we'd like to have curves in our linear models. Again, need to point out, linear means additive, not there's a straight line. In linear models, we can have curved relationships, for example, via polynomial regression or via basis splines. There are more ways of doing this, but these are definitely the most common. Polynomial regressions are characterized by global effects of each parameter, meaning each parameter bumps the relationship in the entire range of the relationship. So you can't switch it on and off at certain points, for example. And these are unable to show monotonic relationships, meaning always increasing, always decreasing, for example, because by definition of how polynomial works, it needs to curve at some point and go the opposite way. So everything that is polynomial second order will have a switchback point at some point. Now, you could argue that, well, but there's one monotonic relationship with polynomials on first order polynomials because they don't have a square in it, for example. Yeah, but that's getting into rhetorics a bit too much for my liking. So on the left-hand side, you can see how you could specify these in math notation and then how they would fit to our data. And you can already see the fit on the quadratic and cubic polynomials are quite more compelling than they are on the straight line that we've done so far, so the first order polynomial. The way to do this in R is on the left-hand side, this time we're looking at height and weight of all of the individuals in the data set of the lecture, because that's where we get this nice curve, a bit more pronounced. And on the right-hand side, you can see that our weight right here has now been entered again, but this has been squared, as you can see up here, and it has been squared from a standardized or centered weight explanation, that is. So this is also Z transformation. Don't know how many of you have used that. I've grown to like it quite a bit because it makes different variables intercomparable, because everything is explained by standard deviations around the mean of that one variable. You can use the scale function on R to do that, for example. So standardizing predictors, like I already said, before model fitting makes our estimations easier and then also helps with the interpretation, especially if you have something we don't have in this session today, multiple different variables which are on different scales, for example. So you might have a length parameter and a weight parameter, which aren't both measured in either meters or kilograms. And if you want to compare the effects of the two, it could really help to standardize beforehand, because by doing so, you get rid of that unit that you would always need to track. Now, the other option which we are left with here is basis splines. And basis splines work in such a way that you have an interpolation of localized functions. So these are also called penalized splines in Bayesian terms, which is abbreviated to p-splines. I think I would just call them splines for now, that's fine. Because in non-Bayesian terms, you call them b-splines for basis splines. And especially with so many German speakers in the room today who are always struggling with hard and soft pronunciation of consonants, at least I do, B and P might become a bit confusing when spoken fast. So the way these work is you have weights which are synonymous with slopes, for example, and then we have basis functions, which are synthetic variables. So these basis functions tell us about the function that we want to look at in a certain region, whereas the weight tells us when to flip it on or off, and more visualization for that on the next slide. So the global function, which we get from B or P splines, is defined by the number of knots, which means how many different functions do we want to connect. So number of knots is how many connection points do we have, and the polynomial degree of the local functions, meaning the basis functions themselves. Now, one thing which is important to keep in mind here, that's why I'm repeating it, neither of these are mechanistic, and they can exhibit very strange behavior beyond the limits of data. That goes both for polynomial regressions as well as for basis splines. So using either of these to predict beyond the bounds of the data that we trained our model on can be very misleading. So for example, using these to interpolate climate change into the 2100s, for example, might be a very bad idea, because that's not what these are built for. So the way we do this in R is this time we're looking at cherry blossom temperature. So tracking the temperature when cherries blossomed in Japan for a very long time, as you can see from that year axis there. We get the data from the rethinking package. We then look at the precise output and the actual data. But as far as the specification is concerned, here's a bit more of a visualization of how splines work. So we get those knots, which is where functions link into one another. But also, we get our basis function. And those basis functions are these paths right here. So for example, this would be one basis function. This would be one basis function. And these can be turned on or off. So for example, right here at this point, the basis function 4 has the maximum weight of 1, meaning this is the only thing that informs our local data, or that we use to understand our local data, because all other weights are set to 0. Now, these weights can be something other than 1 or 0 respectively, if you move to the left, for example, which is why we fuse the estimates of the different functions together, thus getting the smooth transition from one single local function to another single local function. The way to do this in R is with matrix multiplication. So this is done to sum the weights and splines together. And the chapter said so, you're not familiar with matrix multiplication, you shouldn't worry about it, so I didn't. And that is basically what I've got in terms of summary for today. Those are my main takeaway points that I went with. So if anyone else took something more out of this chapter or wants to add some clarification, please go for it. Otherwise, I'm just going to transfer us into the practical session. Cool, that doesn't look like that's the case. So I'm just going to stop the share and take you over to my second screen and open up the book. So the way we've done this, could I just get a quick show of hands? I can't see you anymore, which is weird. I think my Zoom bugged out. Can you guys still hear me? Oh, there you are. I think my internet just took a dump there. Yeah, okay, cool. I can see all of you again. Could I just get a quick raise of hands of how many of you managed to go through the practical examples? And don't worry if you didn't. Just, I would just like to know how many people managed to go through the examples. That's cool. Halfway done is also fine. So the way we've done this last time was just alternating between people of just going through, did you solve this one? Did you solve this one? You take this one, you take that one. I propose we do something similar again today, just so everyone gets to weigh in a bit and I get to take a sip of water in the meantime. So since two of you only had, I assume that Sam and Anna, you went through the easy examples and you managed those.
Yeah.
I started.
Cool. In that case,
and then I got stuck at the end of the medium ones.
That's totally fine. That's what we're here for. In that case, Anna, would you be fine with taking over for the easy ones? Then we'll have Sam do the medium ones right up until where he got stuck, and then Gregor and I will take over from there. Does that sound good to everyone?
Yeah, I can start with what I have. So with the easy ones, you mean the 4E.1, right?
Yes, I will just quickly share the screen to show the book for that, so that everyone in the recording, unless you've written that down yourself, so that everyone can see what the question was.
I have it just on a piece of paper, actually.
Cool. I will just share the screen then. There we go. Floor is all yours.
Okay, perfect. So the first one was asking for which of these terms is likelihood, which is, I think, the first one, because the other ones are parameters. So that's what I assumed. I don't know what the others say.
Completely agree.
Okay. And the second one is actually asking for how many parameters are in that same term, which I already said, right? Which are 2, the one in the middle and the one in the bottom. So mu and sigma.
Cool. Exactly what I've got to.
Okay. So I need some help with the third one. I left it out.
All right. Using the model definition above, write down the appropriate form of Bayes' theorem that includes the proper likelihood and priors. That one, I will admit, I'm just going to flip to this. Can you see my browser now? Or did I share
yes.
just Mendeley? Yeah. Why do you even give me the option of sharing just programs? Okay, there we go. So now you should be able to see it. I've done that right here. So I've just followed the example on page 87 for this. Personally, I have to say I did just do a copy and fill in the blanks job here. I did not bother to understand this. And I don't know if any one of you did. Gregor, I think if anyone, probably you. I didn't think this was very useful.
Me neither.
Yeah, I left it out.
Cool. Okay, so there's the solution to look at it, but it doesn't seem like any one of us cared enough to really understand this. All right, taking you back to 4E4.
Okay, so 4E4 was one I could even answer without this book, which was asking for which one is a linear model, which is the second. I think we've all seen this lots of times.
Yep.
And then the fifth question is actually also concerning these terms, asking for how many parameters are in there. So now there's alpha, beta, and sigma, so I'd say 3.
Cool. Yeah.
Okay.
I don't really think there's much to add there. Just for anyone who hasn't worked with these practical examples, so that would be Paulina and Carl, was that too fast? Did you get what we did here? And if not, please just jump in and voice discontent right away. Also, Ollie, sorry, Ollie, you didn't show up on my sidebar. Same goes for you.
Understandable, and I just have myself to blame for not going through the examples. We'll do for the next.
Everyone does that on their own time. If you don't manage to go through the practical examples, still just show up and talk about it. There's really no blame there.
Sorry, I don't know whether I was aware of this. What do you mean by your sidebar? Oh, I mean, this is the first one I've attended.
Yes, sorry.
So,
yeah, sorry. I meant by sidebar. I meant all of the different video screens. So I couldn't see earlier whether you had raised your hand on whether you went through these. So and for a second there, I forgot you were here, and I'm terribly sorry about this. It shan't happen again.
That's fine. Yeah, no, that wasn't too fast. I'm just still getting used to all the sort of the Bayes language and just sort of getting comfortable with it. So, but that was fine. Thanks.
Cool. All right, going on to Sam with the medium 1 question.
Cool. Do I just share my screen?
Yes, I will stop my sharing, and the floor is all yours.
Cool. Let's see. Did that come through?
Yes, it did.
Yeah.
Perfect. All right. For some of them, I wrote down the questions. For some of them, I didn't. I'm pretty sure medium 1 is basically just asking you to simulate a bunch of priors.
Exactly.
If I remember. Runs of this, so we can just run through this code here. Here we can simulate our means, simulate our actual height data. And this is what I have. Does that look right by anyone's suggestion?
Sorry, 1 second. My Zoom just dropped. Give me just 1 second.
You're all good.
I guess the recording has gone in as well then. So I guess we. Oh no, it's
still recording. I think it's still recording.
Well, I hope the recording went through my drop of Zoom as well. We'll see. Sorry. Give me 1 quick second to look at what you've done.
The formula.
So it's just this for medium 2.
It is the same model as above.
Right. You already went to
M2.
Yes. Cool. Sorry, Gregor, you were saying?
That's absolutely correct. What is there? Like, this is the quad formula for the model specified above. That's
perfect. So then we had medium 3, which is basically just going the other way around, which was, I think, easier, where you go from what is written in R to what you have. And then this is where I did this morning, and I just got frustrated. So this is what I wrote down for 4. Here we're essentially given a problem, and we've got to write down, I think in mathematical notation it was to begin with, what would be a good essential model to run here. Now I essentially copied what I did here. So you got height, normally distributed with a...
Sorry, Sam, 1 second.
Variance.
One sec, Sam. I'll just quickly read out the question for the people who hadn't had a chance to look at them. But I think I'm about to drop again. Hello? Sorry, can you guys hear me again?
Yes, you're back.
God
you're back.
damn it.
You're back.
Sorry, my Zoom just keeps crashing on my end, and I have no idea why. So if I'm
You're
just
all good.
if I'm just gone, just continue on without me. For now, I just wanted to read out the question before Sam went further into his explanation, because I thought that some people who didn't progress to that point may not have known what this was about. So
yeah, if you could do that, that'd be great, because I didn't copy it down.
Totally on it. So the question was, a sample of students is measured for height each year for 3 years. After the 3rd year, you want to fit a linear regression predicting height using year as a predictor. Write down the mathematical model definition for this regression using any variable names and priors you choose, and then be prepared to defend your choice of priors. So we want to model height of students by years in which we have measured them starting from a certain year.
Yeah.
All right, take it away.
Thank you for doing that. Thank you for doing that. So the first 2 lines, I think, were the simplest to write down. So we have a height, and it's normally distributed about a mean, and it has a standard deviation. That mean is what we're fitting into a linear model. Right now, I just wrote this. Where it got a bit tricky for me, and with alpha, beta, and sigma, what we actually write down here. So I thought they were wanting us to write down actually something numeric and play around with it. But I'm like, I'm not going to guess the height of a student or the standard deviation of a class. So I just wrote down these, and I'll see what you guys wrote as well, because I just didn't know what to do. So I had alpha starting as the mean height at the very beginning. I was guessing maybe to start with a large variance here, just to make sure that we're not getting rid of anyone. Beta, this would be the mean growth rate. I'm guessing that we'd want to build a
Sam, could you de-share your screen?
What I have,
yeah.
should I share my screen?
I
Of course.
Why you chose the numbers that you did, because I think what got me was more beta. Why you the second number for beta would.
I'll just share my screen for share to you. Okay. So this is question 4 and 4. So what I have for the prior on alpha is I have used 150 for the mean and standard deviation of 20 because, so I should add that I've used the printed version, the text, the book version for the 2nd edition, which is somewhat different from the online version that you've added to the folder. So that might be the reason why I've some differences in my solutions. So what I experience that is really helpful is plotting the priors, each individually, and then doing some prior simulation as well, which really helps for deciding which prior to use. So for each prior, so for the prior for alpha, I just plotted it quickly, and you like this is just a rather flat prior because we don't know whether the data we've used here, the students are children or if they're high school students or I don't know. So we're really not certain about that, and that's why I use quite a wide range, high standard deviation for alpha, if that makes sense. Like you can see that it reaches from some 100 centimeters to 200 centimeters. For beta, I actually used the uniform distribution. If you noticed it when you went through your example, but we want a positive growth rate, a positive beta or slope of the linear regression. We get this by uniform or by an exponential distribution. Now distribution uniformly distributed between 0 and for sigma, this is just a rather flat trio for ranging between 0 and having a standard deviation of 30, like shown here as well.
If I could, on beta, the slope where you went with uniform, I went with normal distributed, but I set the standard deviation relatively slim or relatively small, so we have a slim curve, because I really like with the normal distribution that everything tends towards a certain mean. However, that being said, and Gregor, you and I, we know that the next questions will lead us to using something else. This is just a starting idea. So I just think there's a case to be made for both uniform and normal here.
Thanks, Gregor. So if I were to redo that, it's best to just play around with prior distributions, because that's where I just got a bit frustrated, because it said build it, and I'm like, I don't know the height of a school child, and I'm like, oh, there's a bit. So that makes more sense now. Cheers.
I mean, that's information as well. If you don't know the height, then that's a prior as well. It's just a flat prior. And like you know something about the height. You can cover the realistic realm with a prior, and it helps really to plot it, I think.
Mm-hmm.
All right, moving on to practice question M5. So I guess now only Gregor, you and I are left to answer questions, or did anyone progress to M5? Cool. Then it's just going to be like last time, back and forth between you and me, Gregor. Since you already did a good explanation on M4, do you want to take over for M5 and M6 as well?
Yeah, of course. Share the screen. So question M5. Now suppose I remind you that every student got taller each year. Does this information lead you to change your choice of priors, and how? Like the information that every student got taller each year basically means that we're dealing with children, because I am a student as well and I am not growing at the moment, I hope. So children are always growing, or rather young juveniles, and you can use this information to adjust your priors. So a mean of 150, which I've used previously, is probably too high for the heat. I've lowered that to 120. And I've adjusted better the growth rate or the slope of the linear model to increase basically the growth rate, because children tend to grow faster than young adults, for example. So what I've did is basically reducing the mean on the height, and keeping the standard deviation the same, because we're not more certain about that. We just know that we're probably dealing with children, which means we're dealing with smaller heights. I've suggested the growth rate a little bit, but you could basically keep it as previously if you want to. There's no reason to change it, if that makes sense. Please just interrupt me if I speak some nonsense. Question 6. Now suppose I tell you that the variance among heats for students of the same age is never more than 64 centimeter. How does this lead you to revise your priors? And I had to look this up. The variance is the square of the standard deviation. And if the variance is never more than 64 centimeters, you take the square root. The sigma is never higher than 8 centimeters. And we can just plug this in our prior for sigma, which I've used the uniform distribution now, ranging between 0 and 8. And then this has implications for the alpha prior, because the spread is not as big as previously. So you could adjust the alpha prior as well, if you want to.
Great. I can see that you've got an I can see that you've got an M7 in here. I guess that is print book specific.
Yeah, should I go through that as well?
This is actually where I have a proposal for you guys, because so far I haven't heard back from any of the potential speakers for next week. So if we don't hear back from them for next week, I would propose to just have a session where we go through practical examples. And if you're fine with it, Gregor, I would reserve all of the non-PDF thingies for that session. So you wouldn't have to do any extra work for that session, but everyone else would have the chance to catch up.
Cool.
Because according to the PDF, we would go into hard 1 and 2 now. I could take that one if you want.
Good.
And I really hope my Zoom stays stable this time. There we go. From one website to the other, basically. So for the first hard question, we got a data frame with some weights. And what the question wanted us to do was then to provide predicted heights as well as the 89% interval, either highest posterior density or percentile interval of these individuals. So fill in this table right here. What I've done for this is I loaded the data, I saved it as D just because this made copy pasting code easier, then put in this list right here, where I now just specified the model as the height has a likelihood of a normal distribution with a certain mean and a certain standard deviation. That mean is determined by our alpha parameter as well as our beta parameter and weight. So this is height regressed on weight. The alpha parameter I have set to a relatively short height with a large standard deviation because we have a large age spread in the data set itself, but also the people in this area are somewhat smaller than the average European would be. So I went with what I would consider to be more childlike height, or very much on the small side for a full-grown adult, and then put a large standard deviation around it. I then set the growth rate, or our slope beta, to be log normal distributed. I wanted this to be strictly positive because I want a strictly positive weight-height relationship. That's what I expect. The heavier you get, the taller you get, especially in a foraging community where access to food, thus weight, should be very determining of your fitness, which could be expressed as height, for example. Next to other genetic variations and such, of course, but I strongly believe there should be a positive relationship here. Then I set a uniform, pretty wide prior on my standard deviation for my likelihood up here, because I don't know. I could have looked at the data. I didn't. I was in a time crunch to get all of this done before we met today. So I figured, I'm not going to do this. I'm just going to put a wide prior on it. Then I plug this all into my quadratic approximation with my formula, and then the data set D. I save this as an object and print it at the same time. That's why I put these brackets around this entire thing. And I get my output right there. Now that I have this, I can obtain the posterior distributions for the weight values in the table. So that's up here. That's what I want to predict for. And to do this, I take my new weights. I then use the link function, which I can use to do predictions. And right here, I say that I want to use my model, which I've identified with the quadratic approximation M, and the new data that I feed it is just my new weight, meaning what's in my table that I want to fill in. Then I just take the mean of the different samples I've obtained. So this is apply the predicted height, every column, and then just the mean. Then I do the same for interval, but this time I want the highest posterior density interval with the 89% spread. Put this all into a data frame. There's a way to do this nicer with cable, I think, to get some tables that look like this up here into the actual output. Here I'm just doing a data frame because time crunch. And you can see that these are the outputs I obtained. Do they link up with yours, Gregor? Cool.
Yeah, perfect. I just wanted to add, I've done the same as it was in the homework for the courses, for the lectures. I've done the same with a quad model where I did not use the logarithm, and I compared the values, and it really makes a difference to use the logarithm of the weight.
Maybe do you have a plot for that you could show us?
Yeah, I can just switch over.
Cool. I will grant you screen sharing rights then.
It's not a plot, but just comparing the both tables. So this is the model with the logarithm, and this is the one without. And you can actually see that where individuals have especially high weight, for example, individual 3, there's a big difference in the predictions for the height. The same for low weights, which makes sense. That's how
so this is edge cases, and I think we'll get into these in just a second on the next question.
Yeah.
I will take us back. That links it really well, though. Thank you very much for testing that, Gregor. So with hard question number 2, we select all of the rows where we just look at ages 18 and below. And then if we do this right, we only have 192 rows in it. Done that, subsetting should be clear to everyone. That works out. So then we have, I think it's 3 parts to this question. The first one is fit a linear regression to the data using QUAP, and then interpret the estimates, and then answer the question, for every 10 units of increase in weight, how much taller does the model predict the child gets? So again, I just built my model here. So right here, I want to look at alpha as the increase, the base height if the child's weight is the mean child weight. So this is my alpha. I assume that the children on average will be 110 centimeters tall with a standard deviation of 30 around it. I put a normal distribution between 0 and 10 on my slope because I know they grow relatively fast, and they definitely grow instead of shrink. So that's why I went with a normal. Sorry, why did I put a normal distribution in there? Sorry, that should have not been a normal distribution. That should have been a uniform distribution. I'm definitely certain I thought of uniform, but just wrote normal, because this is my increase in height per increase in weight. And I really wanted this to be, this was me going too fast for my own good. This should be uniform. I'll change that. And then I have my uniform prior for my standard deviation. Now, because I already stumbled on this one, Gregor, what did you set for this one right here?
I've used log normal with mean 0 and rate of 1, standard deviation of 1.
That's actually a lot better still than a uniform one. Yeah, I'll change that. I guess the effect wasn't very big though, was it? When you contrasted with my output,
there's basically no difference. Yeah.
Okay, well that means that the priors were weak enough to be altered greatly by the data.
The data speaks for itself.
But interesting. that shows you how arbitrary priors can be sometimes. That being said, I wanted something else than what I did here, and that's on me. But yeah, we run our quadratic approximation on this with the data that is subset for just the children. And then we run persist, so we can get this output right here of B, which is our beta. So we can say that for a 10-unit increase in weight, we see a 27.2 increase in height. So this number times 10. Easy as it can get. Part B then asks the question of us to plot the raw data with height on the vertical axis, Y, and weight on the horizontal axis, X. Superimpose the QAP or MAP, because this is maximum a posteriori regression line in 89% and the 89% highest posterior density interval for the mean. Then also superimpose the 89% highest posterior density interval for the predicted heights. So what we do here is we identify the weight sequence along which we want to do the predictions. So where we want to have our predicted mean, the uncertainty for the predicted mean, and the uncertainty for the predicted height. I just did this from lowest weight to highest weight in steps of 1. You could make this as tiny as intervals as you want. I just went with 1. We then use the link function to do our predictions on this. We identify the mean, again, by applying the mean function to this. We identify the interval by applying the HPDI function to this. When simulating the full predictions, we need to use the sim function, again, on the exact same data as before. So the intervals that are already established. And to then get the interval for this, we again just apply the HPDI function with probability set to 0.89. And then we all just plot this exactly like it was done in the lecture or in the book. So we plot our base data itself, then we plot the mean line, we plot the HPDI interval for the mean, and then we plot the HPDI interval for the predictions. So part C, as the last one to this question, we are asked what aspects of the model fit concern you. Describe the kinds of assumptions you would change, if any, to improve the model. You don't have to write any new code, just explain what the model appears to be doing a bad job of and what you hypothesize would be a better model. And this is where we get into the comparison to a logarithmic model, for example, or even a polynomial one. Because what we can see right here is that at both lower and upper end of the weight spectrum, we overpredict the height quite significantly. However, in the mid-range spectrum of the weight classes, we underpredict the height of the individuals, meaning this straight line right here is probably not a good solution, and I would go for a second-degree polynomial to fix this. Gregor, I guess you got to the same conclusion. Would you fix it in any other way?
I would use a logarithm, because with these polynomials, I don't know if you have heard about the polynomial model in, I think, either America or England, where they tried to predict new corona cases in like 2 or 3 months. And one of the employees said that, well, in 2 months, there are no coronaviruses anymore, because he used a polynomial regression for that. And he predicted 0 cases in a bit of time. And following that, that model, in 3 months, we would have negative corona cases. So basically dead corona patients walking again. So like with these polynomials and predictions, I'm always a bit careful. So just using a logarithmic regression here would make more sense, I think. It would be on the safe side.
I think that all comes back to early in the summary when I said that polynomials and basis splines do a really, really terrible job beyond the bounds of the data.
Yeah.
Yeah. No, good point. I will give this over to you for H3 and H4 if you're fine with it. And you're muted, by the way.
Can you hear me again? I can't actually. Yeah, cool.
Yep.
I just have to look up the shortcut because I can't unmute it with the mouse anymore, strangely. Suppose a colleague of yours who works on anometry glances at the practice problems just above. Your colleague exclaims, "That's silly. Everyone knows that it's only the logarithm of body weight that scales with the height." So let's take your colleague's advice and see what happens. That's, well, basically what we just discussed previously. And the part one, model the relationship between height and the natural logarithm of weight. Use the entire Howell data frame, so adults and non-adults, and yeah, then interpret the estimates from the model. So what I've used is I think I've used the priors from the chapter for the QUAP, for the quadratic approximation, and then just looking at the outcome. The alpha is non-interpretable anymore because we're using the log, so you have to think about that in a way. Alpha is now the predicted height of an individual with the weight of 0 log kilogram. Beta shows the predicted increase for a 1 log kilogram increase in weight. So the slope, but now divided by log kilogram, and the standard deviation is around 5 centimeters. So just looking at these these estimates from the model output is, I think, not sufficient, and you can't interpret it really well anymore. So again, here would be wiser and better to plot the model predictions, the posterior predictions of the model, instead of just looking at numbers, which are now, of course, harder to interpret because we've transformed one of the variables. The part two begin with this plot, where we plot the height versus the weight, and then use samples from the QUAP and then to superimpose the plot. So basically what you just done before with the linear regression. This is the plot we're starting with, just all data points, children and adults, the height on the y-axis and the weight on the x-axis. What I've done is, as I've transcribed every code used in the chapter in my own, like in tidyverse way, just that I can understand it better. But tidyverse verbose, so I've written my own functions. Otherwise, all of these codes would, like, the functions are explained above. But what I'm doing is I'm just giving a sequence similar to the sim and lim functions in the chapter. And then I calculate the HPDY and the mean, and the HPDY, the percentile interval of the prediction, posterior prediction, and plot this, and you can see the result here. And it's a much nicer fit to the data now. You can see that the lower values are predicted well, the medium values as well, and the higher values. So it's I think quite a nice result. And the good thing about this is that I even think that you can get some mechanistic understanding from the log here in this model. So some biological understanding, if that makes sense. Should I go on with 4H4?
Yes, please.
So 4H4, plot the prior predictive distribution for the parabolic polynomial regression model, so second order regression model, by modifying the code that plots the linear regression prior predictive distribution. Can you modify the prior distributions of A, B1 and B2 so that the prior predictions stay within the, sorry for the typo, within the biologically reasonable outcome space? That is to say, do not try to fit the data by hand, but do try to keep the curves consistent with what you know about height and weight before seeing these exit data. So just have to switch to the homework because it was basically the same question there. So homework. Number 3. So what I do is I've standardized the variables, so the weight and the weight square. And then I've just used the same model definition as in the chapter with the same priors here. And you can see 2 betters for the second order polynomial equation. And then I've used the extract prior function, which samples prior values. By default, I think 1,000 or 10,000 prior values from the model definition, which somehow feels weird for me because the model already used some data, but it's basically the same as the extract samples, but just with priors. And I've written my own function that is dependent on the priors I use because I want to play with them a little bit, and the number of predicted curves as an argument because I want to see how that affects it as well. And this is just mostly the same code as in the chapter, just adding the plot function here in the end as well. So if you throw some A-list into this function, it gives you a plot using the priors here to fit the model. And here I've adjusted. Now I just need to check how I adjusted the. Yeah, these are the default priors for the model. This is the output for 40 trend lines, and it seems a bit too high for me. So the mean for all of these prior predictions would be around 190 or 80, it seems. So I decided I would decrease the mean a little bit, but increase the standard deviation to express my uncertainty about the data. So I decreased the mean to 130 and increased the standard deviation to 35 for the mean. And this is the result. It looks nicer now. We're expressing our uncertainty about the data in a better way now, because we just don't know where the real height is. Now, the next step was to fuss about the slope. So for me, there was just like, in this case, we're expressing no relationship, or we're expecting, as we're working with priors, we're expecting no relationship between height and weight a priori. So I wanted to increase the mean for the log norm for the first beta in the polynomial equation, to basically force some positive relationships between height and weight. This is the result. But as beta 1 and beta 2 are both equally affecting the slope of the trend line in the end, you should basically adjust the second beta as well to get some curved relationships between height and weight. And this is what I just did here. Like using another density distribution for beta 2, which is now normal with a mean of 0 and a standard deviation of 0.5. And now you can see some of these trend lines are curved more or less, which I think is now a nice result, and I ended with this. And the nice thing about this example is that even if you have some really weird or even flat priors that don't make sense, the regression will still give you reasonable estimates, the QUAP, because there's so much data that the estimates will always be the same. The data just speaks so loudly that the priors are not sufficient to change the estimates in the end. But I think in the lectures, McElrath says that later on we will see examples where the prior are really important, and we should make this kind of simulating what happens when we change the priors, because they will really make or break our model in the end. Okay.
That was fantastic. Thank you very much for that very concise rundown of it. So we're done basically for today. Just quick heads up from what I'm planning for next week. And I'll put this all into an email later today as well. I think that was all up on your website, Gregor, right? Cool. I think I'll just go through the list of the questions you already answered, which were in the print version, but not in the PDF version. I'll put those together so that everyone has them available to prepare those for next week. I'll put that all into an email. I really hope the Zoom recording didn't corrupt today, but we'll see about that. I mean, you were all here, so it's fine. And yeah, if I can get a hold of one of the speakers for next week, we'll have a speaker attending. If not, we'll just have a practical session and talk about our applications amongst each other. So with that out of the way, all I'm left with is getting my speech impediment right today, and also wishing all of you a happy weekend and looking forward to seeing you next week.
Thank you so much.
Thank you. Bye.
Thanks a lot.
Bye.
Bye.
Thank you. Bye.